Hello everyone, in this video I'm just going to give you the solutions for actually a previous main exam paper, okay, from last year, so in 6B. So you can see the question, if you add them up you will get about 17, okay, so that's 70 marks altogether for this question itself. So if you have already watched another video, which is the question 1 in the tutorial 8, okay, so you probably have already got some idea about how to solve this question. This is because this main exam question is very, I would say, very similar to the question 1 in tutorial 8 document. Okay, so you can see that all these 4 questions, okay, so here we need to calculate the specific enthalpy of steam at the inlet of the nozzle. Okay, so that's specific enthalpy, so that's H1, so this is inlet, so that's H1. Okay, and now we need to calculate the specific enthalpy of the steam at an outlet, so that's H2, and here specific volume of the steam outlet, so that's C2, sorry, that's V2, specific volume, that's V2, and finally determine the exit area of the nozzle, A2. Right, okay, so if we have a look at the question, so this is a question Q1 in tutorial 8, okay, so if we compare these two equations, we'll find that they actually exactly the same with these questions here. So in this question 1, you ask to calculate H1, H2, V2, A2, okay, and in this question you are asked to calculate exactly the same thing. Okay, so what's the difference thing here is that if I look at the question itself, actually the first word will tell you what's the difference. So for this exam question, it says steam enters a nozzle, right? And here for question 1, so it says air. So this makes difference between the different working fluid, okay, because for the steam is not an ideal gas, okay, so for the steam we cannot use ideal gas equations to find out any properties. So what we're going to use? Yes, we're going to use a steam table, right? We're going to use a steam table to find the steam properties depending on the inlet and outlet conditions. Basically we need to know the pressure, temperature at inlet and at outlet, and make use of that steam table to find out the properties such as, you know, the specific volume or the specific enthalpy. So all this information we need to find out. So let's have a look at together then. And then again I'm going to make a list of all the information I can get from the from this question. Okay, so first of all, enters the nozzle operating at a steady state condition with P1. So we know P1 is 40 bar, T1 450, velocity C1 30 meter per second. Okay, so these are all the, you know, the inlet variables. The heat transfer can be neglected, so the Q is 0, okay, and okay, the heat transfer can be neglected. There's no significant change in potential energy, means delta P dot E dot is 0, okay, and the steam leaves the exit, so we're now listing all the variables at the outlet, so we'll give it a subscript of 2, okay, with outlet pressure, so that's P2 is 20 bar, C2 is 220.4 meter per second. So these two are at outlet. So we're going to make a list of these also information for the following calculations. And so first of all, we're going to determine the specific enthalpy of the steam at the inlet of the nozzle. So we're going to find out H1, okay? H1. So this is, as I said, this is not like an ideal gas, which we can, under what circumstances we can use, the ideal gas equation to find out, to calculate H1. But for steam, okay, because we know the pressure, 40 bar, we know the temperature 450, and then we need to make use of a steam table. And first of all, actually, we need to find out what the phase or the status of the steam is actually at the inlet, okay, according to the pressure and the temperature. I think we have done quite a lot of practice on that problem, and then we just have a look again. So we need to find out the pressure, which is a 40 bar, okay. So this is for saturated water and steam, so we can use that to find out the TS, which is saturation temperature first of all, so at exactly 40 bar, okay. So at 40 bar, the TS is 250.3, right? So we can make a note here. So at 40 bar, okay, TS is 250.3 centigrade, okay, 253.3 centigrade. So I make a note because I want to make a comparison between the temperature given here, which is the 450. You can see that temperature is much higher than the saturation temperature, means that the water at this condition, okay, under this condition is a superheated vapor. So we need to make use of the superheated vapor now. So we need to turn to so this is still saturated water and steam. So here, okay, so superheated steam, and then we need to find out 40 bar and 450 centigrade. So 40 bar, we have 40 bar here. Okay, 40 bar, and the 450 degrees here, so this column, okay, this column until we reach 40 bar here, okay, and then we have a group of 4 data here, okay, and the first one, specific volume, specific internal energy, specific enthalpy. So the third one is specific enthalpy, which is 3330. Okay, so that's how we're going to find out H1, which is a superheated 3330 kilojoule per kilogram. Okay, so you just get 2 points, okay, 2 marks once we find out the value of H1 from the steam table. So that's it. And the number 2. So now we need to apply in steady flow energy equation. So that's just another name for that first law of thermodynamics in closed system. So this long equation. So if we introduce those assumptions, especially for a nozzle, because we're looking at a nozzle at this case, so this is a nozzle, and then we can write the simplified equation, especially for nozzle, right? So you can find out in the lecture slides the simplified form for nozzle is written in this way. Okay, and then we're going to calculate H2 based on this equation. I'm just going to move this term to the right. So H1 at half C1 squared subtract C2 squared. Okay, and we know H1 is 3330. Okay, so this is in kilojoule per kilogram. So now we have done quite a lot of practice on the unit problem here. Okay, so you need to remember that. You need to make these two terms, the units of these two terms, consistent. So C1 is here, and C2 is here. Okay, so we can use 30 squared subtract 200, 620.4 squared Okay, and then we need to divide it by 1000, as I already explained in the previous question. So this, because this is a cubic, this is SI base unit. Okay, however, we have a kilojoule here. So if I divide this one, then both of these will be in kilos, right? So, and then we can calculate H2, which gives us an ounce of 3138 kilojoule per kilogram. So that's for the second one. The third one. So the third one is asking us to find out the specific volume of the steam. So we're looking at V2. Okay. So I would say that this is a little bit tricky one, and we have no direct measures to find out the V2, to be honest. However, we need to think about, because we know, first of all, we know that inlet, I just explained, and the inlet, so that's a superheated steam. Okay, so how about outlet? Okay, so we need to find out the phase of that steam at the outlet. So is it a wet vapor, or is it still a superheated vapor? So we need to make sure about that first of all. So we have some clue here. That's because 20, so the pressure at the outlet is 20 bar. Okay, so we can use the steam table to find out. So at P2, 20 bar. Okay, we can actually check the Hg at 20 bar by using the saturated water and the steam table. So at 20 bar is here. Okay, 20 bar, and we know HF, that's HF, that's Hg. Okay, so if it's a wet vapor, means that the wet vapor, the specific enthalpy of wet vapor will fall in the range between this and this column. Okay, according to different pressure. So if you have 20 pressure here, okay, under 20 bar, we know HF is 909, and we know Hg 2799, which is about 2800. Okay, so at the pressure of that, we know Hg is 2799 kilojoule per kilogram. Okay, as I said, we know that at the outlet, the pressure is 20 bar, and if the steam is a wet vapor, so the enthalpy should be smaller than that. Okay, however, the enthalpy we just calculate from the previous step, 3138, is bigger than that. So this Hg is smaller than H2. So this actually gives us some clue that the outlet steam is superheated. So this superheated steam. Okay, so just use Hg and H2, so we can compare them, and then we get this conclusion, right? So this means that we're still going to use the steam table. We're going to use a superheated, okay, superheated steam at the pressure of 20, okay, at the pressure of 20 bar. So according to different temperature, so the temperature is varying from 250, 300, 350, 400, 450, 500, 600. Okay, so this is according to pressure of 20 bar. So you can see that we have enthalpy here, enthalpy. So you need to make sure that the enthalpy we just calculated is 3138. Okay, so if we look here, 20 bar. Okay, the third is H. So all these 9 is H's. Okay, and then your final one, which is exactly same as 3138, is here. Okay, so this is actually another way. This is not the normal way we're using, but it's another way that we find out if the enthalpy, specific enthalpy, is given as 3138 as we calculated, and then we know that it's under 20 bar. And if we have look upwards, then we know that the temperature is actually 350. Okay, 350. So we know that the temperature at outlet is 350. And actually at the same time, because once we find the location of that outlet, which is 20 bar and 3138, so there must be this group of data. And you can see that the first one, 0.1386, is exactly actually the V, specific volume. And this is at outlet. So we can directly get V2 is equal to 0.1386 cubic meter per kilogram. Okay, as I said, it's a little bit tricky because the way the way of we using steam table normally. Okay, so normally we know the pressure, we know the temperature, and then we find out H2. Okay, however, in this case, we know the pressure. We already calculated H2, and based on P2 and H2, then we find out what temperature it is. So it's a little bit different way, but according to the steam table, especially for the superheated steam, at that temperature, we found that the enthalpy is exactly the same as 3138. So we can decide the temperature here, and at the same time, from the steam table can find the specific volume, especially under that temperature, under that pressure. Okay, so this is how we're going to find out. It's not a calculation, so it's just found out by the steam table. So this is the third question, specific volume. So that's V2, and we already found out the V2 here. Okay, then let's have a look at the final one. So the final one is exactly the same way as the previous question Q1. Okay, so we're using exactly the same method. We're listing that formula first of all. So m dot is equal to A2 C2 divided by V2. Okay, and then we need to calculate A2. Right, we'll just rearrange it. So it's m dot times V2 over C2. So m dot is 3 kilogram per second is actually here. Okay, so 3 times V2. V2 was just found from the previous step. Over C2, so C2 is here, okay, 620.4, right, which gives us our final answer. And also we can convert that to centimeter squared. You don't have to do that because the question didn't ask you to write in a unit of centimeter squared, so it all depends on you if you would like to write that in another unit. Okay, so this is basically all for questions. Okay, I would like you to compare this question in tutorial 8 document with the first question, just to find out the difference and the similarity and the difference between these two questions. Okay, because the only difference is that in a question, the working fluid is steam or air, so we need to think about for under different cases or how we're going to find out especially the enthalpy. Okay, for steam, we're going to make use of the steam table.